That is essentially the northeast shore of the Black Sea. We've never made it to my board, I guarantee you.
Okay. Let's come to order, please. All right, absolutely. Thank you. Okay. Are we good with the warm-up? Do I need to say anything else? I'm going to make it go away in a second. Is Luke right? Not right? Luke has a comment. Go.
I put plus or minus 1 because I have this TI-83. I didn't store the value, so I rounded the point immediately, so it kind of screws up every answer.
You don't have... Okay.
It's 150 point something. I forgot the store.
Is that right? 150 something?
Yeah, or 151 if you want like 360.
151 degrees to 360? Okay. All right. We'll just trust him on that. The others are right. You guys like those? Okay. All right. So let me say, and this will help us answer a question from yesterday as well. We didn't get to my last slide yesterday, so let me say what work is real quick, and then we'll proceed with today's lesson. I'm sure you looked this up in the book, or you saw it on my PowerPoint too, or something like that, that work is defined to be the scalar that results from having dotted the force vector with a displacement vector. So this is like the one application we're pointing to as we think about the dot product. There are others, but you've probably heard of work before, and you've probably even computed it if you've taken a physics class or science class of some kind that required that. This is how your book presents this kind of problem, so I'll model this example after that, and then I'll send you back to try those homework problems, those last two, I guess, again, and see if they go better for you, okay? So we've got some force acting in some direction and displacement happening in another direction. And just on the face, that might even be uncomfortable for you, right? But I just want to make sure you understand why that actually does make sense. Like if I'm dragging this chair across the floor, if I apply a force like this, and I displace it, its displacement might be in this direction, even though the force I'm applying is in some other direction, right? In fact, you can even quantify how much of my force is acting in this direction. And the answer is, how much of my force is acting in that direction? Well, it's the amount of force I'm applying at this angle, the amount of force I'm applying in this direction, times the cosine of the angle that I had formed with the ground, right? Because it's only that piece that I'm applying. You know, if the cosine is 0, then that means I'm not applying any force in this direction. I can't move the chair that way if I only move it up this way. So that makes sense. So if I want to increase the amount of force I'm using in this direction, then I need to lower my angle, get the biggest cosine possible, right? Anyway, all right. The point is, displacement and force are happening in two different directions, and work is defined by the dot product of these. Sometimes in a science class or something like that, physics class, they might have just said work equals force times distance or something. Technically, these are vector quantities. Technically, it's the dot product. Okay, so tell your teacher that. Okay, it's the dot product is what it should be. Are you ready to do it? We need a force vector. We need a displacement vector. Find the work done by. All right. So can we come up with a force vector given this information? Right here. Right there. In the 2-3 direction, that just means like in that direction, and then throw away the magnitude. Like that's just trying to characterize the magnitude. That would be the same as saying a 15 Newton force acting in like the 4-6 direction. They're just trying to characterize, you know, with this magnitude, can you make a vector that is in this direction with this magnitude? That's a problem we did in that first night homework too. Do you remember how to do that? The force vector is going to be 15 units long, 15 newtons, in fact. And if we want to make the magnitude of this vector not what it is currently, but what this is here, then we just need to multiply 15 by a unit vector in that direction. Do you remember this idea? So the unit vector in the direction of 2-3 is the same vector 2-3, but divided by its magnitude. So this is just one way to approach the problem. And what's the magnitude of that vector? Something. 4 plus 9 is 13, right? So I claim that this vector right here that I'm about to write down, 30 over root 13, and 45 over root 13, I claim that that vector is our force vector. that it's in the direction 2, 3, which is not hard to convince you of, I think, right? Aren't you convinced that it's in the direction 2, 3? Because it's some scalar. In the end, I've just multiplied a bunch of scalars by the vector 2, 3. So it's definitely still in this 2, 3 direction. It might take you a little more work to convince you, though, that this is 15 units long. But I promise it is, because this is 1 unit long here. I'm multiplying it by 15. You can check. You can check the magnitude by vector. It is 15, promise. Okay, and then let's do the same thing with the displacement vector. What are we doing? 4 meters in the 4, 1 direction. Again, there's nothing sacred about that 4, 1 vector. Just using it to, we're going to strip it of its magnitude now. Divided by 17, root 17. So our displacement vector will be 16 over root 17, comma 4 over root 17. And then if you want the work, then you dot these two. And if someone can get that for us, that'd be great. It's a little bit messy here. We'll give just an approximate answer on this. I can get my calculator. We're just not numbers here. Numbers here are not super. So I'll reach for my calculator on this. Plus, in the end, I want an answer that's like kind of real world-ish. All right, so 30 over root 13 times 16 over. Okay, so I might have typed that in wrong, but you tell me. 44.4 is what I'm getting? Okay, so 44.4 approximately. 44.4, and, okay, upper next level discussion. Here we go, are you ready? What are the units? We have here, this is newtons times meters, and then we have newtons times meters, and then we add them together, and we get newtons per meter. Excuse me, newton meters, right? So newtons times meters is the unit, right? Which is a fine way to leave it if you like, or if you're really cool, you might call them joules. Yeah. Newton meters is good though too. Yeah. Yeah. How did I do it? Yeah, just a refresher. So what is this thing right here, or this thing here? True. What does that give you though? It gives you a vector in this direction, but now like stripped of its magnitude information, in this direction with only 1 unit long. And then we multiply it by 15, that will give us a vector still in the direction 2, 3, but now exactly 15 units long. And same thing with displacement. Now there is another way to do this problem that I just want to highlight, but it amounts to you doing exactly the same amount of work. You'll see, right? So the other way to do it would be like if you wanted to compute the dot product, you could. At first, especially, this feels maybe even better. Especially someone were just to be like, hey, I did 15 newtons, I applied 15 newtons of a force, and I displaced an object at a distance of 4 meters, and the angle between the force and the object and the displacement vector was 20 degrees or something. Then this would definitely be the way to go, right? Because you could just do this second piece and just plug that in and call it a day. In particular, though, for this one, I don't know that it amounts to less work too much, but the nice thing about this is that the force and the distance vectors, we know their magnitudes are 15, that's the magnitude of the force, and 4. And then the cosine of the angle between them, by that formula we gave you the other day, yesterday, is 1 vector, 2, 3, and 4, 1 dotted. And the vector, the angle between these vectors will be the angle we're looking for over their magnitude. Remember, isn't that the cosine of the angle? Okay, but can you see already why, and this comes out to be the same thing. Okay, can you see why that in fact doesn't say that conceptualization is useful and also right, but it doesn't save us any work algebraically. It's exactly the same things we just did. Can you see it? Look at it.
Yeah.
I mean, don't you end up doing the same stuff? In the end, you're computing. Except it's all like in one calculation? Yeah. But in the end, it amounts to you doing exactly the same set of work. All right, so that's just my force discussion, my work discussion done. Let's talk about something else. You ready? Go back, yeah. Go back and try those 2 problems in the homework from last night, and I think you'll find yourself being amazing and showing yourself that you've got great success. Let's keep going and talk about 3-dimensional vectors today a little bit, and the cross product in particular. We'd like to do all of that and more. Where's my clicker? Okay, so the title of the lesson today is Vectors in 3 space, as in 3 dimensions, and the cross product. So we're going to define one more way to multiply quote-unquote vectors today as well. So the first thing we should say is that vectors in 3 dimensions obey basically all the things we already talked about. So for example, I'm just going to run through these real quick. The magnitude formula looks like that, right? And if you wanted to find the magnitude of a 4-dimensional vector, it would be pretty easy to see how that would be done as well, though slightly harder to visualize maybe. The dot product. Can we do that with 2 3-dimensional vectors? That is something, comma, something, comma, something, times something else, comma, something else, comma, something else. Yeah, it's pretty clear, and I think, again, all these formulas, I'm just throwing over here real quick, because I think all of them you'd probably come up with yourself. These 2, you'd be like, yeah, I think I can just guess that that's what's going to happen. And you would be right. And since the magnitude and the dot product are defined in these ways, and we have a good understanding of how to find the magnitude or the dot product of 3-dimensional vectors, then that's all that's needed for this formula here when we were talking about the angle between yesterday with the dot product. Can we do everything that this says over here? Yeah, so that's kind of interesting. We'll be able to find like the angle between 2 3-dimensional vectors as well using the same technology as yesterday. Yeah.
Can you multiply a 2-dimensional vector with 3-dimensional?
Not in any meaningful way, no. Nope. So, and then the other thing I would put on here is like a little visualization of what we even mean by 3 dimensions, right? Like it would be good to start like showing you some pictures of what 3-dimensional vectors mean. We have the x-axis, the y-axis, which you're familiar with, and then we add, you probably really thought about it a little bit, you added something called the z-axis. And the vectors, the unit vectors that we introduced earlier are I, j, and k, the unit vectors in the directions of the x-axis and the y-axis, and now we're adding this like vector k in the direction of the z-axis. So we might even need to go back and rename I. It's really, instead of 1, 0, it's 1, 0, 0, right? And j was now 0, 1, 0. And k is this new vector 0, 0, 1. So we'll start using I, j, and k now as well. But everything that we've said before applies now also, and also 4-dimensional vectors or 5, whatever. To visualize the x, y, and z axis together, I'm going to draw this picture actually right now again, but I just want to show you how it kind of comes about in my mind. I might draw the x and y axis like this, x, y. Can you imagine doing this? It's like you drew x and y, and then tilted it down. That's what this is supposed to. I know the angle it's hard to generate 3 dimensions from on this drawing on the board, but I've like kind of tilted it down. This piece of paper that I was holding that had the x and y. This is only the positive and the positive x-axis and the positive y-axis. And then I took my pencil, aka the z-axis, and I went right through the origin, stabbed it through the heart, and I get this thing. Do you like that? Does that make sense? So this is meant to be. These are meant to be 90-degree angles. We're looking like into the corner of a box almost. And the arrowheads are all coming out at us, out of the board. Yeah. So that's what this illustration is attempting to do, and not maybe doing like your favorite job of. I mean, the best way to do it would be to like do it in 3 dimensions and then be able to like spin it around, which was completely possible. We could like pull up an applet online and we could show you how that might look. But No, not necessarily. I mean, but it is fun to try, right? So here's how they're doing it. I might actually even say this, like if you wanted to draw the vector 3, 4, 5 or something like that, you might do it this way. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. And then you might do this, which is like what you did back in the day when you first learned about the coordinate plane back in, whatever, middle school or something. You might like locate this point by using not like two lines and making a rectangle and putting the point at the corner, but you'd be making like a rectangular prism to locate this point. You see my rectangular prism? Okay. Take some drawing skills. Well, it's just a bunch of parallelograms. Don't be scared. And then there's the point 3, 4, 5, right? And if you wanted to draw the vector, you might draw it from the origin out to there, right, with the arrowhead pointing out to that point. But it's unclear if you just didn't have that box, like what that is, where it's located. But now, you can kind of see, since it's at the corner of a box, you can actually kind of get a sense for the dimensions there a little bit. Don't worry about too much of the drawing skills here. I mean, I think it's good to try to visualize this stuff, but it's sometimes hard. Yeah, first.
Oh,
yeah.
Oh, alright. So why are the axes like Z and then X and then Y? Is it always drawn like that?
Yes. Yeah. Well, okay. I should say with a little bit of an exception. Sometimes, so you're welcome to rotate it other ways. This is the way I like to draw it, but you're also welcome to rotate it so that X and Y go here and Z goes up here. That's a good way to do it. You can even rotate Z. I like to think of Z as up, but there's nothing wrong with rotating it down. The only thing that would just be plain wrong for us would be to draw it this way, and to switch the X and Y axis. You get something called a left-handed coordinate system, which is not the same as either of those. You can rotate all you like, but you can't do this because there's no rotation of this picture that produces this.
So it's okay to have like Y on top and then Z in the
It is actually, but the way I'll always think about it is with Z being up. Yeah.
So, like, does that mean it also, like, any vector also creates, like, 3 angles with the x, y, and z axes?
You could think about it that way. Yeah.
And so the z-axis is, like, perpendicular to x and y, right?
The z-axis is perpendicular to x and y-axis, yeah.
How would you find the angle of the direction of the vector in 3 dimensions? Would you have like the angle from the x-axis?
Right. It does. Now, the magnitude still makes perfect sense, right? Because we just said you just extend this square root of right, whatever. But the angle is no longer the direction. Like establishing the direction is not quite as clear. It actually only takes 2 angles to establish the direction, right? It's like kind of the shadow in the xy plane and then the rise, and those both are. That's called spherical coordinates. When you give in 3 dimensions, instead of giving 3 coordinates, x, y, and z, you can give those 2 angles followed by a magnitude r, and that's a great way. It's called spherical coordinates, and you'll study lots more about them in multivariable calculus when you take that someday. Yeah.
Is it possible to like graph on paper the negative and the negative line?
Yeah, sure. I mean, you might do dotted axes behind, but I mean, eventually, we're just like our skills just eventually fail us a little bit, right? We do the best we can. Don't worry, we won't like tread too far into that waters. It is good, like I said, to talk about. Just think about visualizing this stuff, but we're not perfect at it. Computers help. Can you guys do this stuff if you haven't already started trying? There's no reason for me to have you wait. Just go. Do both these, everything. Give it a try. Yeah. Yeah, certainly. I mean, the magnitude and the angle of a 2-dimensional vector is really polar coordinates, which we haven't really talked about yet this year. Those 2 angles we talked about are like latitude and longitude up here. Just the distance of our away from the center never changes on that. So that always 4,000 miles. We just wouldn't see it. When you get any of these answers, just check with people next to you. Say, person next to me, what did you get? This is what I got.
So was that a projector that turned up because it's basically
Onto the screen, right? Right.
Oh, was it?
Oh, yeah. Sorry, I didn't mention that. We're going to move the proposal deadline to Wednesday because it sounds like everyone's needing a little more time to think about it. You can still turn it on Monday.
No, not that. If you draft it. Would that be more than? If you think about it, because like, if you're like doing that point of view.
But I have like everything done when I
Yeah, and then you'd be projecting onto like a spherical shell. It's still possible. I think it's hard about it. All right. The answer to the first one is. I mean, what's the dot product though? 9. Okay. And so no. Yeah, no is the answer. The answer to the second one is. Does it come out to 0? Cool. That means they're orthogonal. And then down here, just to show you that the head minus tail works here, AB, rather, whatever we're doing, is equal to B minus A. So do it carefully. -1 minus 4 is -5. 7 minus -2 is 9. 0 minus -5 is 5. And the magnitude of that is something. 5 squared plus 9 squared plus 5 squared is equal to something squared. Something, the square root of something. 50 plus 81, 131? All right, and you could round that to something. It's 11 something, right? Oh, good. We'll call it that. All right. Questions, comments about the things we've been doing here? Like, there should surely be no surprises here. Yeah. There'd be a second angle. That's what we were talking about up here. You could define like the magnitude along with 2 angles. One that would be like it's the angle that you would turn, and that would be like the shadow in the xy plane. And then a second angle to tell you how much to rise, right? If you imagine I tell you the vector needs to be this long. The vector needs to be this long. And I need you to turn it, my instruction would be like first turn 45 degrees in standard position in the xy plane. And then rise up 60 degrees, and now you've suddenly like positioned it correctly and you found the vector. Trick. We're not going to talk about it, but it would be easy to, you'll see. Try it. Don't ask me. You can do it. I know you can. Okay. All right, we're ready to introduce the cross product. We really need to say this right now here. So the cross product is finally something we can say because it's, interestingly, and you'll see why in a second once I tell you the physical interpretation, is defined only for 3-dimensional vectors, okay? So we couldn't have told you about it earlier. We're going to tell you about it now. Cross product, notice, is represented by a cross symbol, and the reason we're like so bullyish about the dot product being represented by a dot is because there's some ambiguity here. We want to like use this to mean this and that to mean that. So normally you wouldn't care which one you did. But in this context with vectors, we do care which symbol we're using. And you're going to be a little frightened by what you're about to see, okay? I just want to warn you. This is a way of multiplying 2 vectors that results in another vector. And I'll have to explain what this means. This will make more sense to you if you had studied matrices. And I don't know if you, some of you maybe have and some of you maybe haven't. So don't worry though, I'm going to hold your hand through the whole process, okay? This is, what I've written here is kind of, you can just think of it for those who aren't comfortable with matrices. You can just think about this as a way to organize our work, okay? A little table here, if you will. You might call it a matrix, and those vertical bars mean like the determinant in matrix world. But again, you don't need to know that either. Okay, here we go. The way I do this is I load the components of vector A and V into these 2 rows in order, and it matters that you put one and then the other. And up on top, I've got I, J, and K, our unit vectors in the X, Y, and Z direction. Then I do the following, and you're just going to have to like trust me on this for now, though we can try to come back and explain some of these things. We evaluate the determinant of this matrix. And one way you can evaluate the determinant of a 3 by 3 matrix is to do the following. I'm going to highlight these things so you can see where they're coming from. You take I and multiply by the determinant of this piece. Do you see where this came from now? So it's, now there's nothing you have to memorize here. And then you do, now this minus might take some work to explain, but you'd have to come by if you want me to come by, if you want to like know why the negative is there. You just trust me again. It's J, it's negative J times the determinant of these guys. It's like you're kind of crossing out this stuff, and what's left over is the piece that we're going to use there. And then plus K times the determinant of this matrix. Now still remains to be said what how to compute these three determinants if you haven't thought about that before, and I'll just tell you in a second here. But let me just highlight those again. Do you see where that came from? I times the determinant of this matrix minus the determinant of this matrix times J plus the determinant of this matrix times K. And in the end, we will get a number times I minus a number times J plus a number times K, which will be a vector. The way you take a 2 by 2 determinant of a little 2 by 2 matrix, and it's okay to learn now, even if you've never learned before, is to multiply the diagonal of the matrix, the product of the diagonal, minus the product of the off diagonal. Do you see how this came about here? And then repeat for the other ones. And then that will be your vector right there. You get a number times I plus a number times J plus a number times K. That's your vector. Yeah.
Wait, why is the last one A1, E2, and then A3, E1?
Oh, which one did I do? This is supposed to be A2? Sorry. There we go. It's just this, again, it's this, the product of the main diagonal minus the product of the off diagonal. Okay? So that's a recipe that right now you're like uncomfortable with, and I didn't like prove anything, and I apologize. I just like borrowed this from high level math and then just shoved it in here. But for now, it'll be fun, and you'll see that we get something very, very interesting as our result. I told you there would be a physical interpretation here, and the physical interpretation is the following. If you have two vectors in 3 dimensions, A and B, then the cross product that you get, A cross B, this new vector that we get down here, turns out to be another vector, a third vector, that turns out to be orthogonal to both of the original vectors A and B. Can you imagine that? You take your two vectors in space and create another vector somehow that like launches out of the plane that the other two live in perpendicularly. Here's a picture of it too, animated. So here's a blue vector and a red vector, and when you take their cross product, you get this green vector, which is the cross product, and it is always orthogonal to both of the original two. The other thing to notice here too is that I just stole this graphic off the internet, so it happens to say this, so I'll mention it. Do you see what this says? It says A cross B is equal to negative A cross B, which is interesting. Maybe in all cases up to this point in your life, you've taken for granted the fact that any kind of multiplication that someone might give you and define for you would be commutative, but that's not true here. A cross B turns out to be not equal to B cross A. But they're close. It's good. It's close. One is the opposite of the other. Okay. And you can even see why that would happen. If you switch these two rows and went through this, you can show that you get just the exact opposite value of each of these. Okay. It's not hard to see that. If you know another way to compute a 3 by 3 determinant that someone might have taught you at some point in your life, feel free to use it, okay? This is the way I'm teaching you right now. It's called cofactors and minors. If we have time, at some point I'll show you a little applet where you can like drag the vectors around and it shows you the cross product. It's kind of fun to see that in 3D. But all right, it's important that before you leave today that we show you one example of a cross product. Go ahead, Charlotte.
I had a question about the moving thingy. Like, why was the size of the vector going up?
Yeah, we didn't. Yeah, we didn't talk about. Sorry, my jokes.
Why is the green vector?
Yeah, so we didn't talk about the magnitude. We did say I did come out and say that the resulting vector will be orthogonal to both of the original. And you're like, yes, I see that, Mr. Chase. But the magnitude also has some meaning for our context. Like, we're not going to care as much about what the magnitude of that vector is, though we can compute it and it would be interesting. But it turns out that the magnitude matters for lots of interesting applications as well. The one thing we could notice as this spins around is when the cross product has a really low magnitude and when it has a high magnitude. What did you notice? Its magnitude is 0 when the two vectors are either what the blue and the red vector are. Yeah, are parallel, right? It's 0. It's at its minimum, and it's at its maximum when they're at 90 degrees to each other, right? Which is, by the way, an interesting thing to compare with the same question and answers that you might get when you're doing the dot product. When is the dot product 0? And when is the dot product at its biggest? Think about it. Okay. All right. Let's compute a cross product. Here we go. So I'm going to load I, J, and K into this matrix. Here's the example we're doing. 3, -1, I'm going to put on top. 2, -1, 0, 4 on the bottom. And again, you're just like, for now, I don't, it's not my favorite thing to do, but you're just falling in line. Obey the recipe, do what I say. Okay, here we go. I don't like doing it that normally, but. So we do I times the determinant of this matrix, -1, 2, 0, 4, minus J times the determinant of this matrix if you were to like block off J's column, 3, 2, -1, 4, plus now K times the determinant of this matrix if you were to like block off the K row, 3, -1, the K column, -1, 4. Sorry, 0. Does that look good? You see what I did there to generate those boxes? Okay. And now I'm taking the determinant of these, which I just taught you today, many of you, for the first time ever. You're taking this product here, -4, minus 0 times 2 is 0. And in here, what am I doing here? 12 minus -2. Yes? And over here, 0 minus 1. -1 times 1 is -1 times -1 is 1, so -1. So what do we get? We get -4i minus 14j minus k is our cross product. And then the thing I promised we're going to check now, that the product of this with either, the dot product of this with either of the original vectors produces, it will be 0, right? Because we said that would be true. So if we take 3, -1, 2, and dot it with our vector, -4, -14, -1, do we get 0? Check. And I want to also check the dot product of -1, 0, 4 with our vector, because I claimed this would happen. Let's see if it does. And I claim that I'm going to get 0 in both cases. Let's see if this would be a good confirmation that we did it right, too. -12 plus 14 minus 2. All right, this should equal 0, too. And the only thing we missed today, is the jokes I have for you on the last slide. So, all right, we'll have to do some jokes tomorrow. And Monday. The homework tonight is this worksheet. It's not just the homework, okay? And I think it says just do the odds or something.
Oh, I thought you meant
Charge for money, yes.
Bye, guys. I didn't mention any of the applications for cross products. Well, many of them is a good example. These are cross product calculation. Now you know it. Oh, it's because I don't like you, sorry.